For most of a star's life, the gravity, which would cause the star to collapse in on itself, and the pressure that pushes outward due to nuclear fusion in the core, is in a delicate balance. Eventually, the star will be depleted of fuel to fuse, and this balance is broken, so the star dies. What happens after it dies depends on the initial mass of the star. In this video, we will be looking into the three possible forms that a star's remnants can have after they die, and the limits to their mass which decides their fate.
Let's start by looking at what decides the star's end state, the Chandrasekhar limit. It is the maximum possible mass that a stable white dwarf star can have. This mass is 1.44 solar masses, which means 1.44 times the mass of the Sun, approximately 2.765 by 10 to the 30 kilograms. So what happens if the white dwarf's mass is above the limit? The white dwarf will become a neutron star or a black hole if its mass is above 3 solar masses. This is because the star will experience further gravitational collapse, because the internal pressure acting radially outwards will be less than the star's self-gravitational attraction. The internal pressure is caused by electron degeneracy, which is an application of the Pauli exclusion principle, which states that two or more identical fermions can't simultaneously occupy the same quantum state. So a limit is placed on the total number of electrons that can occupy an energy level in a given volume. Therefore, as the star contracts, electrons have filled the lowest energy levels, so must fill successively higher energy levels. At progressively higher energy levels, the electrons move at faster speeds, generating an outwards pressure known as the electron degeneracy pressure.
If the mass of the star was below 8 solar masses, the dying star forms a white dwarf. A white dwarf is small, with a size similar to a planet, and is a very dense star that has a faint luminosity due to a release of stored thermal energy. The Sun and stars of similar masses will end up as white dwarfs. They are so dense because only electron degeneracy pressure halts the star's gravitational collapse. However, a white dwarf will not exist forever. A white dwarf has no internal fusion, and hence no internal energy source. It will cool down as it radiates energy, eventually having too low a temperature to emit significant light or heat. The core crystallizes, and it becomes a black dwarf. We have treated the white dwarf as the end of a star's life instead of a black dwarf, since the universe is too young to form black dwarfs, so they are a theoretical end to stellar evolution.
Moving on to stars with an initial mass greater than 8 solar masses, there are two possible endpoints: neutron stars and black holes. Above the Chandrasekhar limit of 1.44 solar masses, the self-gravitational attraction of the star is greater than the electron degeneracy pressure. Therefore, the star continues collapsing in on itself. As the star contracts, electrons no longer fill higher and higher energy levels, but are forced down by gravity to combine with protons, forming neutrons. Upon further contraction, the neutrons are forced to fill higher and higher energy levels. This creates a pressure, the neutron degeneracy pressure, which halts further collapse. At this point, a neutron star is formed. Neutron stars are much smaller and denser in comparison to white dwarfs. Therefore, they have an incredibly strong surface gravity. To put this into perspective, the surface gravity of a neutron star is up to 3 trillion times that on Earth. If the mass of a neutron star exceeds a certain limit, the star will inevitably continue collapsing into a black hole. Such a limit is called the Tolman-Oppenheimer-Volkoff limit, or the TOV limit, which is around 2.2 to 2.9 solar masses. This TOV limit for neutron stars is analogous to the Chandrasekhar limit for white dwarf stars. A black hole forms when the force of self-gravity is greater than the outwards acting neutron degeneracy pressure, which causes further gravitational collapse. At a certain distance from the singularity of a black hole, the escape velocity of a mass is the same as the speed of light. This distance is called the Schwarzschild radius. At distances less than the Schwarzschild radius, even light cannot overcome the gravitational attraction of the black hole.
In summary, we discussed the three stellar remnants: white dwarfs, neutron stars, and black holes. Generally, small sun-like stars evolve into white dwarfs, and the Chandrasekhar limit is the upper bound of mass for white dwarfs. Stars with greater mass form neutron stars, where the upper bound in this case is the TOV limit. Finally, black holes form above the TOV limit.